Out here in our universe, one of the most energetic and catastrophic events is occurring: the collision of two black holes. I'm Miguel Bezares, an assistant professor at the University of Nottingham, and today we're diving into the fascinating world of binary black holes that inspired the artist Konrad Shokros. Black holes are among the most mysterious and intriguing phenomena in the cosmos. They are born from death of massive stars, and occasionally, two of these remnants find themselves locked in a cosmic dance. They orbit are not static. Over millions of years, these black holes inspire inward, losing energy through gravitational waves. These waves are ripples in the fabric of space-time that propagate at the speed of light. When their dance ends, it concludes with a dramatic finale. The two black holes collide, merging into one large black hole, and the energy released at this moment is immense. Gravitational waves carry information that light cannot. They reveal the mass, the spin, and even the history of these black holes. They have given us a new way to observe the cosmos, the new era of gravitational waves. Einstein predicted them theoretically in 1916, but only 100 years later, on 14 September 2015, the first direct detection of gravitational waves occurred. This was a historical milestone for science and led to a Nobel Prize in Physics. Nowadays, large interferometers observatories like LIGO in the USA and Virgo in Italy can detect this wave and tell us the history of their journey. Finally, why do we study binary black holes? Because they are a window into the extremes. They test Einstein's theory of general relativity under conditions we cannot replicate on Earth. They also inspire the next generation of scientists, like me, to push the boundary of what we know. The history of binary black holes is one connection, evolution and discovery. As we contemplate the artwork in this exhibit, let it remind us of the unseen force shaping our universe.
So this artwork engages with the idea of the multiverse, which sounds like a crazy concept from science fiction, and it is, but it's also something that a lot of physicists are deeply interested in and really want to get to grips with and understand, because if it's true, it could radically change our understanding of the universe and our place in it. And one of the ways that this idea of the multiverse pops up in physics is through the creation of bubbles. So just in the same way that, in your kitchen, you can take some water and boil it on the hob, and you'll see at a certain point the liquid wants to start turning into a gas. So the water wants to change from one state into another. And the way that it does this is by just a little spherical blob of it will just change into the new state, so turn from a liquid into a gas. So, in a completely different setting, 14 billion years ago, right at the kind of very early stages of the universe's history, we think a similar kind of process may have happened with a quantum field, so one of the fundamental building blocks of nature. And what we think may have happened in these kinds of theories is that this quantum field starts in one state, but it wants to transition to another, and so it makes a bubble. The difference in this scenario is that the inside of that bubble is where the Big Bang happens. So everything that we can see, everything that you and I are made out of, all of the stars in the night sky, all of that happened inside one of these bubbles. So that in the early universe, when these new bubbles are being created all the time, just like the bubbles of gas on the hob in your kitchen, these are like baby universes. And so that really, all of these bubbles everywhere, this is just some enormous multiverse of which we can only see this little patch of it. And I really love how this artwork engages with that idea and imagines these two different physicists living in different bubbles within this enormous multiverse. But both of them are looking at these patterns underlying their reality. They're both looking at nature and trying to grapple with it and understand what their place is in the bigger picture. And that's what physics is all about.
Hello, my name is Cameron Bunney and I'm an EPSRC Doctoral Prize Fellow in the Gravity Laboratory in Nottingham. At the University of Nottingham, we are lucky to still have the original blackboard that Einstein used during the lecture he gave here on the 6th of June 1930. Einstein's talk focused on aspects of general relativity and space-time and their implications for physics, and likely emphasized their elegance. Begriff des Körpers is an artwork inspired by this science. The work's central sculpture is created from fabric and wire nets and alludes to how massive objects like black holes curve space-time, a cornerstone of Einstein's general relativity. Now, this curvature not only governs the motions of planets and stars, but also connects to deeper phenomena like black holes and quantum effects in curved space-time. The journey towards our modern understanding of the universe began with Copernicus, who proposed the heliocentric model. The Earth and the other planets orbit the Sun. Kepler then refined this with his 3 laws of planetary motion, showing the planets trace out elliptical orbits. These models reshaped humanity's perception of the cosmos. Building on these foundations, Newton developed his 3 laws of motion and the concept of gravity, explaining why the celestial bodies move as they do. Newton's equations described a universe of 3 spatial dimensions with absolute time, a framework that persisted for nearly 250 years. Einstein transformed this paradigm by introducing space-time, a 4-dimensional fabric where space and time are interwoven. Massive objects like stars distort space-time, creating the effect we perceive as gravity. This insight explained planetary motion, predicted the existence of black holes, and even described the origins of the universe.
My name is Silvia Schiattarella and I'm a PhD student at the Gravity Laboratory in Nottingham. I will talk about the very early stages of the history of the universe and the subject that captivated the artist Alistair MacLeod in his work in the exhibition. The study of cosmology helps us understand the origins of everything we see today, from large agglomerates like the galaxies to the very small atoms composing our bodies. Grasping how matter was formed billions of years ago is an essential step to learn about the history of our cosmos. At first, the universe was cold and empty. All the energy was contained in one single entity, the inflaton field. Cosmologists introduced this quantity to explain an initial phase of rapid expansion of the fabric of space, called inflation. After this phase, the universe transitioned to a hot dense state full of particles known as the hot Big Bang. Following the theory of preheating, this transition would have started once the inflaton field began to oscillate like a pendulum, transferring all of its energy into the fast production of particles. Something very similar happens in fluid systems. In our experiment, we consider a water bath that we shake vertically. As we oscillate the system, we will observe the emergence on the surface of one wave. This wave will then break into the formation of smaller waves covering the whole surface of the bath. In our experiment, we exploit this analogy between cosmology and fluid dynamics to mimic the phenomena leading to the formation of the building blocks of matter as we know it, and to address some of the most crucial questions about the primordial stages of our cosmos.
Hi, my name is Sreelekshmi Chitradevi Ajithkumar. I'm a PhD student at Gravity Lab in Nottingham. Today, I would like to discuss something truly fascinating: light interferometry. In this gallery, we have an actual light interferometer which the scientists and students at Nottingham have created out of Lego. This helps us demonstrate the principle of interferometry to the public or schools. Light interferometry is a technique that employs light to measure incredibly small distances with unbelievable precision. When talking about light interferometry, it's helpful to think of light as waves, like ripples on water. When waves cross, they have the potential to either combine to form bigger waves or to cancel each other. Depending on the situation, they form unique patterns. This is what we call interference. In light interferometry, we take a beam of light, here it's a laser light, and we split it into 2. One part is reflected from a mirror at a known distance, and the other part is reflected from an object whose distance we want to find out. These beams may be called reference and probe beams respectively. Upon recombining, the differences in their path lengths create interference. This principle allows us to estimate distances as tiny as a fraction of a nanometer, which is 1/1,000,000th of a meter. Now, why should this matter to us? Interferometry has applications in industries which require a high degree of accuracy in measuring distances. One of the most famous interferometers is a Michelson interferometer that measured the speed of light back in the 19th century. The same exact principle is used in LIGO and Virgo interferometers that first detected gravitational waves, proving a prediction made by Einstein over a century ago. This won the team a Nobel Prize in Physics in 2017. So that's light interferometry using light to measure incredibly small distances. This shows us even the tiniest interactions can help us unlock the wonders of the world around us.
Hi, I'm Goodwin, and I am an experimentalist here at the University of Nottingham, and I'd like to share some of the physics concepts which have inspired the quantum lens artwork, which is being presented by the studio above and below. To begin, I'd like to talk about quantum entanglement. In quantum mechanics, particles are described as waves, and when two particles interact with each other, these waves combine into one. This new single wave persists no matter how far apart these particles are then separated in space. During the 1930s, this concept troubled Einstein greatly, and the reason is quantum superposition. Superposition is a curious feature of quantum mechanics, in which a particle can have multiple mutually exclusive properties at the same time. One example is that of a spinning particle which can be simultaneously spinning clockwise and counterclockwise. However, when we observe the particle, it can only ever be seen as spinning definitively in one direction or the other. It's as if the particle suddenly decides to spin to the left or the right, but only when we choose to look. This is the so-called collapse of the wave function, and it leads us to ask, if two particles are described by a single wave, if we choose to observe one and collapse that wave function, how does it affect the other? In what he described as a spooky action at a distance, Einstein showed that the collapse of the wave function should affect both particles simultaneously, even if they are at opposite ends of the universe. Nearly 100 years later, we are only now beginning to learn how to make use of this strange quirk of nature. One technique is called ghost imaging. This is where we can generate an image of something without ever having light directly interact with the object. Ghost imaging instead uses entangled light beams to create an image, and it's useful in areas where traditional imaging may not work so well, such as trying to see through thick fog, observing a delicate experimental sample, or even quantum communications. Probabilities are everywhere in day-to-day life. Will it rain tomorrow? Who's going to win the lottery? Heads or tails? All of these questions invite us to make predictions based on probabilities, but in principle, I could answer all of these questions accurately if I had enough information ahead of time about, say, the motion of a rain cloud or the position and momentum of a coin during a flip. Probabilities are everywhere in quantum mechanics too. The difference is that they are baked into the processes themselves. And no matter how much I know about the state of an atom or a subatomic particle, I can never predict exactly what it will do next. I can only predict the probabilities of different outcomes. Particles exist with a probabilistic mixture of different possible attributes, like being in two places at once or spinning in two different directions at the same time. It's only when we choose to look that the particle decides which of these behaviors it wants to show us. This counterintuitive behavior is at the heart of modern quantum cryptography, specifically in quantum key distribution. If I encode a key or a passcode and send it to you in a string of photons with some delicate set of probabilistic states, you will know if it's been intercepted by a third party. The very act of their observation will make irreparable changes to that state and alert you that your data has been compromised. If I run into a brick wall 100 times, chances are I give myself 100 headaches and the wall remains unfazed. This is an obvious fact of life, and it's due to energy. If I don't have enough energy to break through the barrier, I'm going to bounce off every time I collide with it. Now, while this may seem like an unshakable law of nature, if an electron were to charge towards a barrier that it didn't have the energy to overcome, there's a small but non-zero chance that it could pass straight through nonetheless. This is quantum tunneling. Now, over the course of the past century, researchers have found ways to use tunneling as a probe into nature, and one example is called scanning tunneling microscopy. In a scanning tunneling microscope, a very sharp metal tip is held above the surface of a material and charged with an applied voltage. Electrons in the material are attracted to the tip, but they don't have the energy necessary to jump across the gap in between. However, due to quantum tunneling, some electrons can bridge this gap anyway, and the smaller this gap becomes, the larger the number of electrons which can jump across. So by scanning this metal tip back and forth across a surface, we can build up a detailed picture of the atomic scale landscape we would never hope to resolve with a regular optical microscope.